We have the 9th sequel in our series of viewing Earth from space, the changing environment and climate of our planet. And I'm very, very happy and honored to welcome Professor Sonia Seneviratne today. Sonia is the professor for land climate dynamics at the ETH in Zurich, where she has completed her master's, but also her PhD thesis in climate science. She was afterwards a visiting scientist at the NASA Goddard Space Flight Center, from where she returned to become a full professor at ETH Zurich in 2016. She's more than 200 peer-reviewed articles and is listed among the highly cited researchers of the Web of Science. In her research, she investigates climate extremes, land climate processes, and of course, human-induced climate change. Sonia has received several prestigious awards for her research, amongst us also the Wackelwain Medal, a consolidator grant of the ERC, the Hans Oeschger Medal of the EGU, and of course, and that she's well known for that. You see the logo on the top right. Sonia was an author of several reports of the IPCC, where she's also been a lead author of the special report on the 1.5 degree global warming, and she was also coordinating lead author of the 6th assessment report. Before I turn the floor to Sonia, I would kindly ask the attendees, the participants to this seminar, to put potential questions into the chat, please, where I will, after her presentation, read the questions out to her, so enabling Sonia to focus on the presentation, not having to monitor the chat. So kindly put your questions in the chat and we'll deal with that afterwards. So again, a cordial welcome to you, Sonia. Really glad that you could make it to be here today. And with that, I would say the floor is yours. And again, thank you.
Well, thanks a lot, Michael, for this very kind introduction. It's a great pleasure to give this presentation. So as mentioned, I will focus here in a large part on the latest IPCC report in which I was involved, in particular on the part 1, which was dealing with physical change in the climate system. And so I will speak about changes in climate extremes and also the relevance of remote sensing dataset for this type of analysis. So as mentioned, I want to focus on some main conclusions from the IPCC report. The first part, which was prepared by the Working Group 1, is dealing with the physical science basis. And I was just one of several authors. You see that we had really many people contributing to this report. We were in total 234 authors. We also had to work on this report in special circumstances since I was in the COVID at the end. And so it was also quite a special experience to basically present the main conclusions of this report in the approval session of IPCC, where we had sometimes teleconference with about 400 participants. I was coordinating the chapter 11 together with Subin Zan from Environment Canada. So chapter 11 is dealing with weather and climate extremes. That's why I will focus on this topic here. It's a specific topic on which there's been a lot of new material in the latest report. We had a really good team working on this report. I include here some pictures of those participants. And you can find the final version of the chapter online. Also want to mention that since then there were 2 other parts of the 6th assessment report of IPCC that were released, also the Working Group 2 and Working Group 3 reports. I will mention some conclusions of those reports as well, and they're also all available online. So I want to start first with what we know about the global change in the climate system and just basically highlighting that we are indeed in a climate crisis. So all the numbers basically point to that. You see here the evolution of the global mean temperature, and we see that we already had 1.1 degree of global warming in the last decade compared to the second half of the 19th century. This temperature level is unprecedented in more than 100,000 years. I mean, we have to imagine that 100,000 years ago, we were still in the Stone Age. Agriculture has been developing since about 10,000 years. So we had actually in over all of this time when agriculture was developing, temperatures that were lower than now. So we are really in a truly unprecedented time in terms of climate change. The largest part of this warming is irreversible for several hundreds of human generation. CO2 stays very long in the atmosphere. Part of the emitted CO2 stays in the atmosphere for several hundred to thousands of years. So the consequences are very long-term. And even if we were to stop all emissions now, we are not going to go back to the climate of pre-industrial time. We are just going to be able to stabilize global warming. I think that's a really important part. Now, the best estimate of the contribution of human emissions is that basically almost all of the warming is due to our emissions. It's not only half of the warming or a quarter of it. The best estimate we have from the report is that about 98% of the global warming is due to human emissions. So there are really no other explanations for this change that has been observed. This is also illustrated here, in which we have climate model simulations, which include only the natural forcing in blue, and then also includes the human forcings emissions. And you see that if you only include natural forcings, you basically have absolutely no change in global warming. And you only get the observed warming if you do include the drivers that were resulting from emissions for human activities. That's why we also have these very clear conclusions from the IPCC report, which is that it is unequivocal that human influence has warmed the atmosphere, ocean, and land. So I want to highlight that the situation is getting worse every month. Basically, for instance, here I just included latest update on the CO2 concentration in the air. Every year, CO2 concentrations are higher, and it was again the case this year. So this is, for instance, an article from the New York Times saying that carbon dioxide levels are the highest in human history. And so this is the latest update where you see this very strong increase of CO2 year after year. And so for the first time this year, we had a concentration of CO2 which was above 420 ppm. Again, the source of the CO2, this excess CO2 in the atmosphere is very clear. It is human emissions, and I insist on CO2 because we have other greenhouse gases, but it really CO2 is one greenhouse gas that has the longest lifetime in the atmosphere. So in terms of the source of those emissions, again, we know very well that we have had emissions for a very long time since basically the start of the industrial era. And most of those emissions, especially now, are due to the burning of fossil fuels. So if you look at the latest estimates, really the largest part, almost 90%, is burning of coal, oil, or gas. Then there is also a contribution of land use change, deforestation. And so that's basically the main problem we are dealing with. If we could get rid, for instance, of all burning of fossil fuels, that basically most of those emissions would already disappear. We would be very close to zero. In terms of the link between CO2 emission and global warming, this link is extremely clear. It was already shown in the last IPCC report, the fifth IPCC report from 2013. Here it's an updated figure of a figure that was already in the fifth assessment report, where you see on the x-axis the cumulative CO2 emissions since 1850, and here the level of global warming. And you see that the relationship is almost linear. The more CO2 is accumulated in the atmosphere, the more global warming we have. And so as mentioned, we are looking at cumulative CO2 emissions since 1850 because the lifetime of CO2 is so long-term that really it's the accumulated amount that matters. Now, this also has implication in terms of what will happen in the coming decades. If we want to stabilize global warming at the level at around 1.5 degrees, which is the aim that was set in the Paris Agreement, then obviously we have very limited remaining CO2 budget that we can emit. After what, it's basically given that we would be above 1.5 degrees. So in terms of the change in temperature in different regions and time, you see here first the variation in time on the left. So that's mean warming per decade in 1900 to 1980, and then since 1981. And I think that's another concerning point, which is that warming is not linear. Actually, it has been increasing since 1980. We have actually an acceleration of the warming since about 40 years. In addition, you have much more warming over continents and in the oceans. This has strong implications, for instance, for hot temperature extremes, for heat waves. You see that on average, the land temperature has been increasing by 1.6 degrees compared to the ocean 0.8. And so as mentioned, the mean global warming was 1.1 degrees. So again, it shows that in specific regions, we have substantially more warming. And you see that one region that is specifically affected is actually Central Europe, which might be relevant to many people based here. So for instance, in Switzerland, we have already more than 2 degrees of mean warming. Regarding changes in extremes, one main conclusion is that the evidence of observed change in extremes has strengthened. So we have much more evidence, and some of this comes down to more science, more literature. But in the end, it's also just more time that has gone by with more events that have happened since the fifth assessment report. So in the last decade, we have had several extreme events that were very clearly affected by human-induced climate change. The extreme events that were assessed in our chapter included temperature extremes, such as heat waves, also heavy precipitation, floods, droughts, storms, and compound events. And by compound events, we mean multivariate extreme events when we have different events of different types happening at the same location, also at different location, but at the same time. One main conclusion is that human-induced climate change is already affecting many weather and climate extremes in every region across the globe. So we find that all regions of the world are affected in some way by changes in climate extremes, and no region is spared. So every region is affected in some way. We also find that some recent hot extreme events would have been extremely unlikely to occur without human influence on the climate system. So we see for many events that some of those events have been made more probable because of human-induced climate change. But in the case of some events, actually, the contribution is so large and those events are so much outside the variability we had in the past that we can say we can only explain these events with the contribution of human-induced climate change. So I show here a few examples of recent events that were made more likely because of human-induced climate change. Just taking a few events from since last summer. I'm sure you remember the Canadian heat wave. There were temperatures of almost 50 degrees that were reached in the region. And you can imagine that's actually quite far north. And there were very strong impacts, burning of forests, and also a city that was burnt in just one day. So very dramatic consequences. And in the same summer, actually, we had also very heavy precipitation in Europe, in particular in Germany, which led also to many deaths in the country. Now, just more recently, next example, there have been a large number of heat waves, but one more example, there was, for instance, the heat waves that happened in India and Pakistan, in which temperatures were reached, which were basically at the limit of what is bearable for human survival. So clearly we are starting to have such events that are really extreme and happening actually also very frequently. In terms of the general statistics, the maps I'm showing here provide overall assessments of where we see observed increase in some extremes, for instance, hot extremes at the top, extreme rainfall, or droughts at the bottom. So all the different hexagons are showing different regions of the world, and all the hexagons that are filled in color in red for the top, or blue or green in the middle, or yellow for droughts are showing actually an increase either in the frequency or intensity of those extreme events. So as mentioned, we see that all inhabited regions of the world are affected by some changes in extremes. Most regions are affected by increase in hot extremes, but also many are affected by increase in extreme rainfall, and a few others are affected by increase in droughts. Maybe not, probably there will be people outside West Central Europe, but for those based in West Central Europe, it's actually one of the regions that is particularly strongly affected. You see here, it's one region that is affected at the same time by increase in heat waves, extreme rainfall, and droughts, but there are also other regions where this is the case. So here I'm just providing a general statement that were summarized in our chapter for specific type of extremes. So as mentioned, for hot extremes, this is clearly the type of extreme for which the evidence is the clearest. So we came to the conclusion and the assessment that it is virtually certain that hot extremes have become more frequent and more intense across most land regions. So we find really in almost all regions of the world an increase in hot extremes. And there is high confidence that human-induced climate change is the main driver of these changes. For heavy precipitation, we have actually also quite a strong signal in several regions. And in this map, it's important to consider that some of the hexagons here are filled in gray. These are actually regions where we don't have so good data. So it's difficult to provide an assessment in those regions. And in fact, if you consider the regions where we do have data, it's clear that over most land area where we have good observations, we see an increase in heavy precipitation, as you can see in this map. We also find that human influence, in particular greenhouse gas emissions, is likely the main driver of the observed global scale intensification of heavy precipitation in land regions. About droughts, we have also a much clearer signal compared to what was available at the time of the fifth assessment report, where only very few regions were showing a signal of changes in drought. Here we have from the observation several regions showing a signal, and on average we find that over land regions there is an overall tendency towards drying in the dry season, so less water availability in the dry season. We found basically assessment for different types of drought. In particular, we focus on agriculture and ecological drought, which is how much water is available in soils, for instance, for agriculture and ecosystem. And that's a type of drought where we find a particular strong signal. And this signal is mostly due to increased land evapotranspiration. So it's not really that droughts are induced by less precipitation, except in a few regions. It's rather that some regions you have a clear increase in evapotranspiration. And so this is drying the soils, which is the main reason for this change in drought occurrence. About other type of extreme events, for instance, we also find a signal in tropical cyclones. So the assessment of chapter is that it is likely that the global proportion of major tropical cyclone occurrences increased over the last 4 decades. And human influence has also likely increased the chance of compounding extreme events since the 1950s. So this is again a new type of assessment where we look at the co-occurrence of different type of extremes in the same location or at different location at the same time. Some of those compound events that have been affected include concurrent heat waves and droughts. We find on global scale, concurrent heat waves and droughts happen more frequently, and that's important for many types of impacts, for instance, for fire occurrence. And so that's why we also have this assessment for fire weather, that we find that there is an increase in fire weather in some regions of all inhabited continents. We also find an increase in compound flooding in some location. So for flooding, it's not only precipitation that matter, but also other conditions that lead to more water at the surface. For instance, if you have an increase in sea level and this combines with heavy precipitation, it leads to more risk of flooding. And that's what is meant by compound flooding when you take into account those different drivers of flooding. So now what will happen in the future? And here I'm pointing to a document that we prepared after the special report from IPCC on 1.5 degree global warming, where we highlighted that really we are at a crossroad where our decisions are really going to matter. We can still more or less stabilize global warming if we take very quick decisions, and there we could maintain a change in climate at more or less the levels that we are experiencing now, where we have more impacts in the past for several type of extremes, but still it's not the type of climate that we know at the moment. But we could have, of course, much more changes in extremes and also change in the Earth system. And so our decision in the coming 2-3 years will be absolutely key. Now, what will happen, for instance, in terms of global warming, you see this here from the projected changes in global warming for different scenarios. So in the IPCC report, 5 different scenarios were considered. And the scenario with least emissions we reach about 1.6 degree in mid-century, and then we can go down to 1.4 degree at the end of century. So we can stabilize global warming around 1.5 degree. But in the worst scenario, we would continue to have further increase in emissions. We would reach already 2.4 degree in the mid-century and could be well above 4 degree at the end of the century. So here you have an illustration of those different scenarios. It shows how much emissions is considered in those different scenarios, and also what is the resulting global warming. You see the total warming on the left for each of the scenarios. And so again, we are really at a crossroads where we can go in different directions. But what is absolutely essential is that there is really only one of the 5 scenarios which is compatible with the aim of the Paris Agreement, which is to limit global warming well below 2 degrees and to pursue effort to stabilize it at 1.5 degrees. This scenario here in light blue. And for this scenario, you see here the emissions. We need to have immediate reductions of CO2 emissions, and we need very quickly to reach zero emissions, net zero emission. In the other scenarios, we can have a stabilization of emission and then a decrease later on, but we can even have a continuous increase of emission. I think that's really important to mention. It's not that we have a limitation of fossil fuels. If we want to, we can continue to emit a lot of CO2. There will be a lot of fossil fuels available to burn for many decades. So if we want to limit global warming to 1.5 degrees, we do need to decide to leave fossil fuels in the ground. We need at some point to really have a decision not to use this source of energy anymore, because else we won't manage to achieve this aim. So in terms of what will happen in the future, in particular after 2030, this will depend really on the change in emissions and on global warming that will result from this, and which can say in terms of extremes, if you mention a possible scenario for the future, we find, for instance, 1.5 degree or 2 degree, we know that with increasing global warming, we have more frequent and more intense extreme events for many, many types of extreme events. So we find that the frequency and intensity of climate extremes become larger with increasing global warming for a range of type of extremes, for instance, hot extremes, marine heat waves, heavy precipitation, agricultural and ecological droughts in some regions, and the proportion of intense tropical cyclones. We have already much higher risk at 2 degrees compared to 1.5 degrees. I think that's one main conclusion we had already in the 1.5 degrees report from IPCC, and it's even clearer in the 6th assessment report that even half a degree of global warming really does matter. It makes a big difference. This means that we cannot say, oh, we don't manage to reach 1.5 degree, then let's aim to 2 degrees. In that case, if we cannot, then let's try to maybe limit global warming to 1.6 degree or 1.7 degree. In the end, one main conclusion is every 1/10 of a degree in global warming does matter. But we should also say that even at 1.5 degree, even in the best of scenario, we would still have more impacts compared to now, because again, we would have more global warming than what we are having now. And some of those impacts include irreversible impacts. There are some changes that are not reversible. For instance, some species loss. Of course, if this happens, we cannot go back. This loss will be basically irreversible. Here, I just want to show how the frequency and intensity of some climate extreme change with increasing global warming. That's from the summary for policymaker. And so you see, for instance, here for temperature extremes over land, we are looking at the frequency of an event that would have happened only once every 10 years without our influence on the climate system. So such an event would happen now at 1 degree of global warming would happen about 2.8 times every 10 years. So it would be about 3 times, it is already now 3 times more frequent than what it was in the past. So we see that obviously already now we have a strong change in the climate system. We're already seeing changes in extremes. But at 1.5 degree or at 2 degree, we are going to have even much more increase. So for instance, at 1.5 degrees, such an event would happen 4 times every 10 years. So more than now, and at 2 degrees, it would happen 6 times every 10 years. So you see that would be double compared to now. And this would mean that actually the majority of the summers would include extreme events. At 4 degrees, it will be almost every year. One other important point is that the change in a very rare event is actually larger in percentage change. So you see that if you look at the multiplication factor, so how much more frequent a certain event becomes, if you look at the 50-year event for heat extremes, so the one event that would have happened only once every 50 years without our influence on the climate system. Such an event has become 5 times more likely compared to 3 times for the 1 in 10-year event. And in 1.5 degree would happen about 9 times every 10 years, and at 2 degree about 14 times. So you have an even stronger increase in those very rare events. Further, we don't have only more frequent events, but those events are also more intense. And this intensity increase is here, that's a mean over land regions for hot extremes. And so you see that the change is larger than what you have in terms of global warming. But in some regions, it would be even larger than those numbers because, as mentioned, we have some regions which are warming particularly strongly. So here I have a similar analysis for heavy precipitation events. And similarly, you see this increase in frequency of events with increasing global warming, and also a very strong increase in intensity. That's a very well-known physical relationship. It's based on the Clausius-Clapeyron relationship. And what we find for heavy precipitation events is that for each degree of global warming, such events on average become about 7% more extreme, so more intense. So they have become already about 7% more intense, but at 1.5 degrees, it would become 10% more intense. So you see this also exponential increase with increasing global warming. Now, in terms of droughts, you see here also changes in frequency and intensity. In the case of droughts, we have less regions affected. So these statistics here are only for those regions which are found to be drying with increasing global warming. But we should say this includes a large number of regions on all continents, in Europe, in North America, South America, South Africa, and also Australia. And so again, we see in those regions this increase both in frequency and intensity of droughts with increasing global warming. So now about compound events, we find also that with increasing global warming, every region is projected to increasingly experience multiple changes in climatic impact drivers, including streams. So I think that's another important point, that we have this multiplication of threats. Before we looked at the statistics, for instance, of change in heat wave or hot extremes and heavy precipitation. And we've seen that, for instance, we would have much more years where you would have hot extremes or heavy precipitation happening on average on land. But you have to realize that the same location in some summer may be affected by some hot extremes and other heavy precipitation. So we would have also much fewer years, which are just normal conditions. And we have had this, for instance, in Europe, where we had, as mentioned, heavy precipitation last year. But for instance, now there is a drought in part of Southern Europe, but also part of Germany. And in years before, we also had heat waves. So many regions are projected to experience an increase in probability of compound events with higher global warming, both concurrent heat wave and droughts and fire weather conditions, also compound flooding, as mentioned before. And another point, which to me is really important, is that we have more probability of having extreme events at the same time in different locations. The application can be also very important for impacts. For instance, you could have more extreme events at the same time in different crop producing areas. And we find this is clearly higher at 2 degrees of global warming compared to 1.5 degrees. This could mean a substantial impact on food security on global scale. Here I include also some other assessments from special reports from IPCC, for instance, from IPCC land report. That's an assessment of the change in risk using the amber diagrams as function of global warming. And white means that you have undetectable risk, yellow means moderate risk, red high risk, and purple very high risk. And you see that at 1 degree, which is more or less temperature we have at the moment, we are at the level of moderate risk. But at 1.5 degree, we would be shifting to high risk. And above 2 degrees, for instance, we would have over 50% increase in the area burnt in the Mediterranean region. And above 3 degrees, we would have we would be shifting to very high risk. For food security, I mentioned before the risk of having different food producing areas affected at the same time by extreme events. And you see also the fact that this change can happen quite quickly with increasing global warming in terms of the implications for risk. So at 1 degree at the moment, we are at moderate risk, but 1.5 degree, we would be already at high risk with periodic food shocks across regions. And above 2 degree, we would shift to very high risk. So again, here, it does make a very large difference if you manage to limit global warming to 1.5 degree, which implies risk, but maybe still manageable risk possibly, and higher levels of risk would get very difficult. So in terms of risk assessment, the main assessment is provided in the Working Group 2 report. I did contribute to the assessment for the risk associated with extreme events, which is shown here in this bar. And I think the main point you see for this different aggregated assessment of risk is that you see increasing risk with increasing global warming, and obviously with the highest risk for unique and threatened system, but also very strongly increasing risk associated with extreme weather events. And so this main statement from this report is important, which is that near-term actions that limit global warming to close to 1.5 degree would substantially reduce projected losses and damage related to climate change in human system and ecosystems compared to higher warming levels, but cannot eliminate them all. And that's related to what I said before, which is, yes, 1.5 degree would avoid a lot of damages, but still it would imply higher risk compared to now. So now I want to say a few words about what are the actions we can take. And we do see we are in a risky situation, and clearly it's time for an emergency break. We have to change the course we are on. And here, that's what we have in terms of scenarios that would be consistent with 1.5 degree. And if you remember the course of emission in the past, they were always increasing. And now we're at about 40 billion tons of CO2, which are emitted per year. And from this figure, which is from the special report on 1.5 degrees, you see that if you want to limit global warming to 1.5 degree, we need to very quickly have a decrease in emissions. And the scenario is still consistent with the latest assessment that was published by the Working Group 3 of IPCC. So stabilization to 1.5 degree requires change which are unprecedented in terms of scale. We need to have an immediate reduction of CO2 emissions on global scale until 2030, a halving of CO2 emission. So we have to have about half of the emissions compared to what we had before in 2010. And we need to reach net zero CO2 emission at the latest in 2040. That's for 66% probability of limiting global warming to 1.5 degree, or 2050, which gives us only 50% probability. Finally, we also need some negative emissions. You see also after we have reached zero emissions, there would be actually some negative emission. And basically this means also taking up CO2 from the air. But at most, we should say it would represent about 10% of present day emissions. So it's not that we are going to save ourselves with negative emissions. Really, for the majority of emissions, about 90% of emissions, we need to bring them to zero. And negative emission compensation through either technological approaches or afforestation can only be used for about 10% of emissions that are very difficult to get rid of. So here I just wanted to give an update on global policy from the last climate conference that took place in Glasgow. And you see that's an assessment which looked at what are the commitments that have been set by different world countries and what would be needed in terms of emissions pathways if you want to follow 1.5 degree scenario or 2 degree scenario. So currently the commitments would stabilize emissions, so at least they are not for an increase of emissions, but we see that we are far away, so that's for 2030, we are very far away from scenarios or commitments that would be consistent with 1.5 degree, or even 2 degrees. So we would need to have much more efforts in terms of change of emissions to be able to be on a 1.5 degree pathway. So clearly we are not on track at the moment. Now I want to say a few words about our remote sensing research, and the datasets can contribute to climate research and also IPCC reports. Obviously, there are a whole range of contribution, and a lot of those contributions are already happening. So I just want to illustrate some main aspects. Obviously, a really important aspect is related to process understanding, and I will show some examples related to the drought effects on vegetations and CO2, which I think is a really important topic, which possibly where we still have some possibly quite relevant uncertainties. Satellite data or remote sensing data can be also used as constraints for climate models to reduce uncertainty in projections. They can also be used for early warning and monitoring of climate extremes. We also need better integrated data sets, such as what is initiated in Digital Twin Earth and other such initiatives. And also an essential part is the verification of emissions. So we need to make sure that we really know what are the sources of different greenhouse gas emissions, and more specifically, for instance, obviously for CO2, but also how much of CO2 emissions is related to fire, also what are the sources of methane emission. I would say in terms of remote sensing data, one main limitation is that we have a general lack of long-term consistent data sets. So for instance, for climate extremes, in the IPCC report, we looked at trends since 1950. And so this means that we have, of course, not really satellite data going back this far back in time. But I mean, even for some general statistic, we need at least 30, 40 years of data, which is quite difficult actually to have if you want to have very consistent time series. So here I'm showing some ways to also overcome this type of issue. This is, for instance, work from Vincent Frey, who did a PhD in our research group. He looked at GRACE data, so from the GRACE satellites, which is measurements of terrace water storage. And in his PhD, he developed a method to reconstruct also terrace water storage time series back in time using basically the satellite data to calibrate a statistical model with meteorological data, and then from this reconstruct also longer time series. So that's a way in which satellite data can be also used to extend the time frame. And for instance, here, this was compared, this reconstruct time series in blue to measurements of global mean sea level with altimetry. On the other hand, we also use this data, for instance, to look at relationship between water availability and the carbon cycle. That's in a paper that was published in Nature 2018. And here you see again the satellite data and then the reconstructed data in light blue. And in black, you see the CO2 growth rate. So it's basically by how much CO2 is increasing every year in the atmosphere. I think you see by eye already that those time series are very strongly related, except for the Mount Pinatubo years, which were excluded because we know we had different radiation conditions. Now, if you look at this relationship between the two data, really you have an extremely strong correlation, as can be shown here. And it shows that when on average you have more droughts on land, you tend to have an increase in the CO2 growth rate. So you have either more release of CO2 or you have less uptake by plants. On the other hand, if it's wetter, it's the opposite. You have actually less CO2 growth rate because plants are able to take up more CO2. So it shows a very clear relationship between water availability on land and change in CO2 in the atmosphere. Now, what we did in this paper was also to compare then the same correlation with other data sets, in particular with terrace water storage computed in land surface models, which are used in Earth system models, these trendy simulations here. And what we found interestingly was that the correlation here is much weaker in those land surface models, which are used actually in the climate models. So I would say this did open really a question to which extent maybe these feedbacks between drought and the carbon cycle are underestimated in current climate models, and whether this might have implication for projections. I would say it's still an open question, but certainly one where, for instance, satellite data did help to point to a possible issue in climate models. The implications are important because we know that with increasing global warming, the land and ocean sink become less efficient but this might mean that actually even here at lower levels of global warming, the sink might be still even smaller than what is being estimated at the moment. Now I want to sort of show a few other examples of applications. One obvious application, and that's where satellite data is extremely useful, is that you have obviously global estimates, and you have also near real-time estimates. So this can be used, for instance, for early warming. One example would be to use this data for better prediction of hot extremes, because we know in many locations that hot days tend to be preceded by drying conditions. And so this means that there is some potential for early warning and forecasting. So this was an assessment based on precipitation deficits and temperature extremes. You see a strong correlation in many locations. And again, this is related to a feedback between droughts and hot extremes, that when you have less water in the soil, you tend to have less evapotranspiration, which leads to more sensible heat flux and higher temperatures. And so using this type of relationship, we find that you have some predictability of whether you might have an above average number of hot days in a given summer or less hot days here. And so this means that there would be a potential for forecasting, which is starting to be implemented in some forecasting system, but I think could be actually used even more. Here, in terms of the relationship in satellite data, you see that there is also a relationship found in microwave-based soil moisture retrievals. It's also showing this negative correlation, so drier conditions, less water leading to more hot extremes. But actually, this relationship is a bit underestimated in this type of data. And the main reason is that microwave remote sensing is only measuring the top soil moisture. So that's a small storage compared to the total storage that is relevant for plant drought, and which can capture better when you have really truly extreme events, as you can see here for one example. In terms of monitoring, this is the first example from a study from Nadine Nicolai Shaw, in which we looked at a range of data sets, to which extent we could find anomalies preceding a drought or following a drought. And interestingly, you see some clear relationship, for instance, that you tend to have a higher ET before drought, and you see also some follow-up conditions. So you see some propagation in different satellite-based and realized products. So I'll go to the next topics, which I wanted to illustrate, which is also the role of dry air versus dry source for vegetation drought impacts, because there's been a lot of discussion of this in the literature. So on the one hand, we know, of course, that plants need to extract water from the soil. On the other hand, there's also literature suggesting that when you have very dry air, so high vapor pressure deficit, this can induce even more stress for vegetations. And so here in this study that was led by Library U in our group, we used solar-induced fluorescence, or SIF data from so CO2 SIF data set to look at whether we find a relationship with SIF, of SIF with soil moisture or VPD. If you just look at the relationships, you find actually a relationship, but if you look at bins here of VPD, you find still a relationship with soil moisture. So it suggests soil moisture is indeed a driver. So you see higher SIF with higher soil moisture, but within single bins here of soil moisture, we actually don't find a strong relationship with VPD. So in this paper, we came to conclusions that it seems that soil moisture effects appear dominant, but this is, for instance, one example of trying to understand what are the main drivers for vegetation during drought. Finally, I also want to mention a new development from our research groups from Verena Bessenbacher. She just published a publication in which she looked at how we can gap fill Earth observation, because that's one limitation we have in remote sensing data, that we have some gaps in some locations for certain products. And so she developed a method to basically intelligently gap fill Earth observation by combining different sources of satellite data sets. So I come to the conclusions. We are clearly in a climate crisis, Extreme events leading to excess deaths are made more probable due to human-induced climate change. And that's one example, but we have impacts of a whole range of different impacts. We already have more than 1.1 degree of global warming. And if we don't decrease CO2 emissions immediately, 1.5 degree will be out of reach. And really, every month that goes by, this is even more true. The first step is that we need to decrease emissions by 50% until 2030. And so now in 2022, this means a decrease of almost 7% per year from now on. Obviously, we are not on track so far. So remote sensing data play an essential role for a range of application in climate research, for instance, for monitoring, for early warning, for process understanding, for model validation, and also as potential model constraints. In this context, long records, which are longer than 30 years, are really essential. So on one hand, you need projects that integrate existing measurements. One example is, for instance, the ESA CCI initiative. But we also need really continuous measurements. So I think we really need to make sure that we have continuous measurements with similar measurements methods for a very long time to make sure that we can use really satellite data also in a climate context. So we need more exchange between the climate and satellite research communities, and this is really essential to make progress, especially in such conditions now where we need to monitor change very carefully. And so I come to the main conclusions, again, taking into account that we are in a climate crisis. Every action matters, every bit of warming matters, every year matters, and every choice matters. Thanks a lot for the attention.
Thank you very, very much, Sonia, for, and I quote one of the participants or attendees who's put it in the chat, for this very inspirational and excellent, but also unfortunately depressing talk. Really, really excellent insights. Thanks a million. I go straight into the questions. There is a question from Marie-France Loutre asking, what about the cold extremes? I remember the case of Texas completely frozen. Is it related to climate change? ? Is it studied as extreme event? Over to you.
Thank you. Thank you for this question. So we had actually in the IPCC report also a box in which we discuss possible changes in circulation patterns which are associated with global warming. So there's been some suggestions that in general, you have an increased persistence of weather patterns, which is related, for instance, to melting of the ice in the Arctic, but there is quite a bit of uncertainty about, how strong this relationship is. So, I mean, if it is the case, it could also lead to more extreme events, for instance, in winter, for instance, because then you would have longer such events. But the conclusions of this assessment was in terms of dynamics, we still have low confidence in terms of what are changes in dynamics. So it's not excluded that we have also an impact on dynamics, which could indeed also impact cold extremes, but at the moment it's still very uncertain.
Yeah, there is a question from Hans Zinnecker, and I'm not sure there is a quick answer to that. What is the physics behind the extreme weather patterns?
Yeah, well, I guess it depends on the different extremes. So well, maybe again, if you're speaking of weather patterns of dynamics, well, the physics underlying this, most of it is fluid dynamics. So it's basically understanding how fluids is distributed in the atmosphere. But I would say, so if we are interested in what are the processes affecting extreme events or affecting changes in extreme events in the changing climate, most of it is related to thermodynamics. So it's not really about the change in weather pattern. It's about the fact that for the same weather pattern, for instance, if you have a high pressure system, which lead to a heat wave, the heat wave will be much warmer in present climate than if we had with no greenhouse gases. So so far we have still little evidence on change in weather patterns, but we have evidence that for the same weather patterns, we have more extreme events, especially hot extremes, drought, due to thermodynamic effects. Yeah.
Right. Gianluca Alimonti is asking concerning the increase of extremes, and he says that the model projected increase that you've been presenting is not matching the observations reported by the CRED. I assume it's the Center for Research on Environmental Decisions, but I'm not sure, on the number of climatological disasters. if not decreasing from the beginning of this century. And if you could address that briefly, would be grateful.
Yeah, so about this question of, well, I don't know exactly what is the data set that is being referred to.
I don't know either. It just says the observations of the CRED, and I only know the Columbia University Center of Research on Environmental Decisions, and there was a publication about psychology of communicating climate change. But as far as I know, the CRED website is no longer active. So I'm sorry, I don't know more about it, Sonia.
Yeah. Well, I mean, what I can say is there is evidence that, some disasters have been increasing, some others also you have less impact because there has been increase in adaptation. But in any case, there is clearly, for instance, the associated increase in heat wave is very clear. So again, if it's a question of damage, it's a different one because it depends not only on the occurrence of extreme events, but also on vulnerability. So that's a different question.
Okay. Roberto Sabia, who thanks you for the inspirational and yet depressing talk, is asking a former colleague from ESA what the process in IPCC reports is to put quantitative data translated into qualitative, such as attribute labels, such as likely, very likely, and medium confidence. Could you give a brief response to that?
Yeah, thank you. So that's really an essential part of the report. So we always say, reports, IPCC reports are not reviews, they are assessments. And really the assessment is about this part. It's basically about the fact that we look at the literature very systematically. And what is quantified is basically actually two elements. So the first one is, to which extent is there robust data? That's the first part. And to which extent does this data, where available, agree? So do you have first sufficient data, some different sources of evidence of different sources? And the second point is, do these different type of data agree with one another? Now, if it's the case that both you have a lot of data and you have a really good agreement, you have confidence. So that's the first step of the assessment, which is to assess the confidence. And so low confidence means that either you don't have enough data to assess a question, or you have data, but the data doesn't agree. And that's where you have a low confidence. Medium confidence means you have some aspect of the available data and evidence that is uncertain, but you have enough confidence to provide a direction of change. And high confidence is when you really have very good data and quite a good agreement. And that's where you can really provide a quantitative estimate. And maybe it's not obvious, but actually the words likely, very likely, they come to the second step when we actually provide a quantitative estimate. So likely means 66% probability, very likely means 90%. And then, for instance, we have virtually certain, that's more than 99%.
Okay. Super. Thank you very much. That was a clear answer. Stephen Spangler is asking, and he goes back to a slide near the beginning of your presentation. In your slide with the global average temperatures since 0 CE to present, there appears to be a gradual decrease from about 1000 CE to 1500 CE. Is the physics of this decrease understood? ?
Yes, I mean, there are variations in different times. I mean, we know that there are different possible explanations for some of those changes, but I think the point, I mean, I'm not a paleoclimate specialist, so I cannot speak about this specific variation, but I would say if you look at the size of this change compared to what we have been observing since the 19th century, it's much smaller. So again, what we say is that you can expect some variations, but the level of change we have had, we can only explain with greenhouse gas emissions.
Okay, Jeremy Land is asking if the recent slowdown in economic growth at the example of China and long-term demographics are taken into account in future emission estimates.
Yeah, so we should say these are not estimates. Again, these are scenarios. So we have different types of scenarios, and the scenarios are called it includes socioeconomic pathways. And so basically, they include different aspects. And actually, we have different types of possible evolution of society. So for instance, in one of the scenario, one idea is that you have a more multipolar world. In another one, for instance, you have a lot of fossil fuel driven developments. And so demographics, for instance, is not the same in the different scenarios. In some, you still have some increase in demographics, some you have less. But again, I mean, these very small scale events like the recent slowdown, no, this is not included because the scenarios were developed at about 2015. So, I mean, they are looking at a long-term evolution. But of course, this can be assessed when we are looking at the evolution of emissions. Yeah.
There's again a question from Gianluca Alimonti, who says that the food production problems that you were alluding to isn't in sync with the few percent yearly growth of the Food and Agricultural Organization FAO worldwide. And part of this growth is recognized to come from higher CO2 atmospheric concentration. Can you comment on that?
Well, I'm not aware of this, that actually some of the growth is assumed to be associated with higher CO2 in the atmosphere. Actually, the literature I'm aware of is mostly saying that it's improvement in agricultural management and also more fertilization, so fertilizers that are actually used. And so it's well known that we have had an increase in food production. But again, this assessment I was providing, these are based on agricultural models that do take into account also this increase in growth associated with changes in practice.
Okay. Marie-France Loutre is going back to the Game Changer seminar we had 2 weeks ago by Chris Rapley with the title Creating Agency to Act on Climate Change. And Marie-France is asking what you would suggest in this creating agency.
Yeah, so unfortunately, I missed this presentation. I imagine the idea is to say, okay, each one of us can contribute in some way, and I would fully agree with this message. Well, it's a good question. I think some of the answers should come, you know, each one of us has probably a different answer, but I would agree. I mean, we are facing an urgent global problem, and each one of us can you know, affect the outcome now in his own or her own way. So, I mean, there's maybe one important point to mention there is that often there is a mention of the footprint which each have, and it's relevant. About 50% of the emissions we are causing are associated with our own footprint. So let's say our decisions, for instance, not to have a petrol car, or if you have a petrol car. So I mean, I would say one first point you can do is just in all domains of your life where you are, you know, your lifestyle induced CO2 emissions, for instance, because you are using fossil fuels, think about whether you could have an alternative. For instance, for a car, do you need a car, or if you really need a car, then an electric car is better? Can you avoid some flights and so on? But I think the other point is really a systemic change, and there, you know, we can also have a strong impact, for instance, by modifying policy, making sure that we have more stringent you know, rules for all of society, also for industry and so on. So I would say, you know, you can, in Switzerland, if I take the example of Switzerland, we have basically direct democracy. We can suggest new laws, and I would say, yeah, I would encourage everybody at the level of their own village, their own canton, try to see where you can influence decision making, and every small gain is something that is really worthwhile.
That's a clear answer, and it does match up with what Chris Rapley was saying. Jeremy Land is asking a question: is climate change exponential in recent years compared to previous years? Will this continue? ?
Yeah, so I mentioned basically the fact that we have this increase in warming since the 1980s. We don't have a specific assessment of whether it's exponential, but what you see is that the emissions are certainly increasing over time, and also global warming is increasing. Will this continue? Again, as the question is not, I cannot answer this question. The question is to you. Will we as a society be able to stop increasing our emissions?
Exactly. Yeah. Jeff Dozier is saying, some of my friends assert that the year-to-year variance in precipitation, mainly snowfall, is increasing. This is hard to see in observations because we need about 30 years to see what the variance is. Nevertheless, the issue is important. What mechanisms would drive increasing variance?
Yeah, so I'm not really aware of this, for instance, for snowfall. So I'm not sure. I would say in the summer, we can expect some. We know that, for instance, dry days tend to get drier and wet days tend to get wetter. So whenever we have rain tends to be more intense. So I did mention this, with warmer air, you can have more moisture in the air. So which means that when you have a rainfall event, you have more precipitation. On the other hand, when you have dry days, it tends to dry more the soil. So certainly in summer, there is evidence of this. I can less comment on the snowfall part. Yeah.
Okay. Tilman Spohn is asking, what are the prospects for a direct removal of CO2 from the atmosphere?
Well, that's also a big question. So I would say there are technologies that have been developed, for instance, to capture CO2 from the air. Actually, one is related to a spin-off firma from a company from ETH, Climeworks. There are other companies. Other way to do this would be to plant trees. But I think if the question is the prospects, I mean, what we have to see is that first, what is available so far in terms of technologies is still very small scale. So it's not impossible to take up CO2, but we are speaking of very small amounts. So basically, the prospects will depend on how much upscaling we have. But again, as I mentioned before, the scenarios from IPCC typically assume that, you know, the order of magnitude would be about 10%. And that's already, I would say, quite a large number compared to what you can do now. Another point is, I mentioned the afforestation. I think there personally, I have quite a bit of concern because it's often mentioned in the public discourse, you know, trying to plant trees and so on. I mean, we need to protect existing forests. That's absolutely obviously play a huge role. But the problem about the idea of planting trees is that, as I mentioned, there is more risk of droughts in some locations. So actually those new forests may not survive, plus the trees need to grow up. Yeah. So anyway, I think the potential exists, but it's limited. The main message would be it's not zero, but it's also not so large. So the main bulk of the effort needs to be reduced of emission.
Okay. I come to the last question from Giovanni Strazzulla, who is asking, how relevant is the role of other greenhouse gases, exempli grazia, methane or nitrogen dioxide?
Okay, yeah, so they're also very important, especially methane, because methane is really a very powerful greenhouse gas. The lifetime of methane is much more limited in time. So, well, it's again a really long question or a big topic to address. Anyways, the answer would be they are very relevant. They affect mostly the short-term change in the climate system. In the case of methane, one main issue is that there seems to be some methane that is not accounted for, where we don't know what is the source of those emissions. That's the main question we have there. So yes, it's relevant, but for the long-term change, as I mentioned, CO2 is the main issue.
Okay. Thank you very much. That brings us to the end. Oh no, here's one more from Amy Maitland. What are the greatest gaps in remote sensing for understanding increases in extreme weather events?
Oh, well, that's also a big question. I would say the greatest gaps, as I said, would be to have, to some extent, long-term data. So, I mean, this will take time to have these really long-term records. Yeah, I think some of the points, and I mentioned this as well, is there is existing data. Maybe we really need to have more efforts in terms of integrating those different data sets. I mean, in terms of short-term progress we could have is to which extent can we develop more integrated data sets, is ideas of you know, merging the different data sets so that we have a truly global coverage of estimates. But yeah, I would say, for instance, for droughts, we have different data sets. None of them are perfect, but maybe you can create a better data set if we optimally merge those different data.
The Amber Soya Amber jumped to help. She gave compliments to your nice talk before, and she said understanding vertical processes like with high resolution, high spectral resolution LiDARs would help, complementing your answer. And I would also put a little compliment with the launch of the Meteosat 3rd generation at the end of this year on 30 November, and next year's EPS 2nd generation launches. We will have much more refined and higher temporally and spectrally resolved sounders and images on board. Here, Jeff Dozier comes again, and I want to read it out as well. Concerning CO2, work by David Lobel and Hank Sugart generally shows that photosynthesis is limited by CO2 availability only in a few areas, e.g. at high elevation. Generally, warmer temperatures decreases the productivity of some crops. So,
yeah, well, yeah, I mean, that's obviously correct. So basically, I mean, this whole question of how do plants react under increased CO2? I think in the latest report, we clearly show, for instance, in terms of changes in drought, that we know at the beginning of a drought, increased CO2 can increase, higher water use efficiency, but in the end, it doesn't really compensate, and that's what we find in the data, that actually, in the end, plants are very strongly affected, both by increasing temperature, but also decreasing water availability.
I have one more question here from Mark Sargent, who is actually running the video today. And rather than reading, I let him ask the question himself. So Mark, come in.
Hi, Sonia, I hope you can hear me, and thanks for your talk. Yeah, you showed regional differences in how much temperatures already exceed the previous average, right? You showed that some regions have been heating up more than others, I think, early on in your talk. So I was wondering whether that kind of local difference can, or whether and to what extent it can be used to verify models of what happens sort of on a global scale, sort of on the fly, right? You make a prediction, and is there the possibility to check locally whether those models are actually working?
Yeah, so I would say in terms of weather mode, not really, because of course a lot of the weather dynamics is more stochastic in the short term. But if we're speaking about mean changes, mean regional changes, yes. So I mean, some of those changes can help understand, a range of processes. Also, in addition to CO2, for instance, the role of aerosols. So in some locations, aerosols have change on regional scale, so they affected this regional response. So we can assess this regional impact. Also, land use change can have a regional effect on the temperatures. So I would say, yeah, definitely the regional response can help understand also assess to which extent the models are doing, correct job of representing processes. One topic I've done a lot of research on is about the feedbacks of droughts on temperature. I mentioned it, and that's actually an area where we used to have a lot of uncertainty in models. It got a bit better, but that's where observation can help constrain this, because we see this increased temperature response where you have droughts, but the exact response is not always well captured by models. So yes, I think this regional footprint can help constrain models.
Super, Sonia, thank you very much. And again, thanks a million for marking this 9th Game Changers series talk on climate and environmental change, which was a real highlight. And it was very difficult to find a slot in your agenda. And thanks very much for making the time. Before I close, I wanted to encourage everybody to look at those game changer videos, climate change, that they are as videos, as YouTube videos, also put on the ISI Game Changer series website, where you can, if you have missed one of the talks or if it went a little too fast, you can revisit them again. And I would really encourage everybody to go back to those videos. The next webinar that we will have will not be next Thursday. It will be before the seminar summer break, be next Wednesday. It's an upcoming webinar on July 12th. And it will be on the first James Webb Space Telescope data and spectra. And that will be next week's series. Then we have a summer break. And after the summer break, we reconvene on the 8th of September with a new theme on captivating cosmology. So with that, I think my announcement are closed, and we are already 10 minutes past the hour. Thanks again for an excellent talk to you, Sonia. I think the recording can be closed, and with that, I would like to also adjourn the